think we're live. We're going to be starting up in just a second. As people start to join, please let me know if you can hear me or not, and that'll help quite a bit. I'm going to try to change the lighting real quick. All right, looks like a few people have joined. That's good. We'll start up in just a short time. Okay, so welcome to the next live lecture for the POSA Concurrency MOOC. What we're going to do today is we're going to go through the implementation of the AsyncTask framework, and that'll give me a chance to talk about some of the topics that are important for the programming assignment you're working on. And we'll also talk a little bit about some other aspects of the assignment. If you have any questions, please don't hesitate to ask them. If you have any questions about the assignment or anything else that we're covering, go ahead and ask them as well. Let me first go and show you some interesting stuff while we're waiting to get started here. All right, let me bring this up. Hopefully you can see that on the screen, which is my browser. I thought I'd go to the class website. There's an interesting discussion that I wanted to bring to people's attention this morning. So the question that arose was, is it actually necessary to use synchronization in the Palantiri Manager release method? If you go and you look at Palantiri Manager, you'll see that it has a couple of methods. It has acquire and release. And this discussion that I'm about to talk about is relevant for both assignment number 1 and number 2. But in particular, for assignment number 1, if you take a look at the documentation for Hashmap, you'll see the following phrase. It says, if multiple threads access a Hashmap concurrently, and at least one of the threads modifies the map structurally, it must be synchronized externally. And then it has a little parenthetical phrase. It says, a structural modification is any operation that adds or deletes one or more mappings. Merely changing the value associated with the key that an instance already contains is not a structural modification. So it turns out that this comment is actually wrong, or at best misleading. So if you don't hold a lock while you're updating the value in the hash map in release, which needs to be modified from, I believe, from false until true, if you don't put a synchronized statement around that operation, then the value will not be promptly propagated to other threads that may be trying to acquire the lock. and for that reason, your program is likely to fail in strange and mysterious ways, especially on multi-processor, more multi-core platforms that have weakly ordered memory models, which is becoming the norm these days. So I did a little digging after reading this comment, and I talked with the guy at SUNY Oswego named Doug Lee, who has written most of the Java util concurrent software in the Java release, and he agreed that the Java Hashmap documentation is incorrect. So this is very important. It's kind of funny. You would think that the documentation after all these years would be correct, but it's not correct. So the bottom line is you have to use a lock around these update to the hash map using a synchronized block. Now, of course, with Java concurrent hash map, this problem is solved for you, so it's not an issue there. But unfortunately, that's not the case for Java hash map. So you have to make sure you disregard the documentation and do the right thing. Speaking of Java concurrent hash map, here's a good place to go to learn a bit more about Java concurrent hash map. And it kind of explains a few things that are very relevant for assignment number 2. In particular, one of the key things you need to do in assignment number 2 is to do atomic updates in order to be able to update the map, update the value of the map from false to true or true to false, depending on what you're trying to do. And the trick to this is to use the replace method. You can see some examples of where replace is being used in some interesting ways that are somewhat similar to how we're using it in assignment number 2. So I strongly encourage you to take a look at this link and to look at the documentation and some of the examples for Java concurrent hash map. That'll help you to understand better what's going on. Okay, so that was just a quick overview of some of the issues related to hash maps and concurrent hash maps. That's a key part of assignment number 1 and assignment number 2. What I'd like to do now is I'd like to talk about the implementation of the AsyncTask framework. So let's go ahead and bring up some code, and I will share my screen, and then we'll talk through the example here in a second. Alrighty, let me share this code. All right, so this is actually the implementation of AsyncTask from Android. This is the latest version. This is the version that's in version M, I believe, Android M, also known as Marshmallow. And you'll see that this is actually a little different from the earlier versions, and we'll see why in a second. I have ever so slightly rearranged the code here just so that it would be a little bit easier to present. But of course, I didn't modify the code. I just rearranged the order in the classes. Oh, you want me to post the link I referenced on Hashmap? Sure. Let's see. Yeah, I'll go ahead and post that after the classes, after the session is over. All right, so let's take a look at the AsyncTask implementation. So let's skip through all the documentation here at the front, and we'll look at the class itself. You can see AsyncTask is it's a generic. It's an abstract generic, and it has 3 parameters. Params is what's passed when you call execute. Progress is what's passed when you call on progress update, or rather publish progress, and that's passed to the on progress update hook method. And then result is what is passed from do in background, and that's what's passed to on post execute. So those are the things that we've got. Alrighty, let's go take a look at the code here. Now, the first thing that they do is they set some constants that are going to be used to give you default pool sizes. Now, these default pool sizes are optimized in a clever way, and you'll see how they're optimized in a second, but they are insufficient to do assignment number 2. And I'll talk about that as we go through that. That's why you have to create your own thread pool executor, and you have to go ahead and pass that in when you do the execute on executor method that we'll look at later. So here's what the counts are by default. They take the number of available processors and they make what's called the core pool size. The core pool size is the number of threads that will always be in the pool. And they make those to be the CPU count plus 1. So most people's devices probably have, maybe 2 cores, maybe 4 at the most, probably not more than 4 is my guess. So the core pool size will be around 5 or 3, depending on what platform you're running on. And then they also make something they call the max pool size, which is basically twice the CPU count plus 1. So that might be 9 or maybe 5, depending on how many cores you've got. And then they create a keep alive timeout value of 1 second. And you'll see how that gets used in just a minute. And then they create a work pool, which is a so-called blocking queue, which is implemented as a linked blocking queue. And that's a linked blocking queue of runnables up to 128. So you can have 128 things queued up on the default thread pool executor until you actually need to block. Now notice that these values are actually different from what used to be in Android. In the earlier versions of Android, they made the core pool size be 5, the maximum pool size was 128, and the size of the work queue was 10. So in the earlier versions of Android, they really gave a preference toward spawning threads. And in later versions, they decided that was too memory consumptive. So they really greatly reduced the number of threads that were there by default and instead made a longer queue. We'll come back and talk a bit more about these things later. Here's the thread factory. This is the one that they have by default. By default, the thread factory has a method called new thread. And new thread is going to create a new Java thread, passing in the runnable, which is the parameter to the new thread factory method. And then it's also going to give that new thread a particular count. And that count is simply the string AsyncTask number sign followed by the count of the thread. So we have an atomic integer that gets incremented every time we make a new thread. And so each thread will have a new name. So it'll be AsyncTask 1, AsyncTask 2, AsyncTask 3, and so on and so forth. The specific names are really not interesting unless you're doing some detailed debugging. But that's the thread factory. And then down here, by default, they create a new thread pool executor, which has core pool size threads that we'll always have, which, as I said before, is probably a number like 2 or maybe 5. Up to max pool size, which is basically twice that amount. And then they have what's called a keep alive. Now, what happens here, this is actually a cached thread pool with a size that can grow. So essentially they have 5 threads that are, or 2 to 5 threads that are always there, and then they can grow up to about twice that amount. And if they're bursts of activity, then this thread pool executor will create new threads. But if those threads are not used for more than a second, then the threads that are going up to the max pool size will be terminated very rapidly. So they only live for a short time. The work pool thread, or the pool work queue, sorry, is passed in as a parameter, as well as the thread factory. The thread factory, of course, is where they're going to actually get the threads, and we see how they do that up here. So that's the thread pool executor you get by default. And we'll see in a second, you actually use this thing by passing it to the execute on executor method. For your assignment number 2, you can't use the default thread pool executor. And there are 2 reasons why you can't use it. Reason number 1 is it doesn't have enough, it may not have enough threads for all the beings that want to gaze. That's one problem, so that would be inefficient. And then the second problem is that it doesn't actually create a being thread, it just creates a thread. So you'll need to be able to create a new thread pool executor, but this will give you a sense of what you should do in order to make the thread pool executor work properly. There's also something called the serial executor, and that's what's used by default. If you have an async task and you say execute, by default, that execute method will run in the so-called serial executor. You'll notice, by the way, that both the thread pool executor and the serial executor are both static. So that means that there will be one of these instances shared by everybody. So it's thread pool executor and serial executor are shared by all async tasks within a given application. Here's the serial executor implementation. It implements the executor interface, which is part of the executor framework. It makes a new deck of runnables, and a deck is just a double-ended queue. You can put things at the end, and you can put things, you can put and take things efficiently at the end. You can put and take things efficiently at the beginning. Honestly, not really quite sure why they used a deck here. They probably could have gotten by just using a queue, but we'll take a look. So here you can see the execute method. This is what gets called back, of course, when you execute something on this executor. This is a synchronized method, so this code in here will execute as a critical section, just one thing at a time. We take the runnable that's passed to it, and we go ahead and we make a new runnable, and we stick that into this deck. So that'll go at the end of the deck. So by calling offer, that'll put it at the end of the deck. And the runnable that we put in there has a run method, which when called, will call to the parameter runnable's run method. So that'll go ahead and call run. So when this method is called, and it doesn't get called here, it gets called down below, it's going to go ahead and run the runnable. And of course, that will run in a background thread. And then over here, what we see is we have a finally method called schedule next. And what schedule next does is, as we see down here, it goes ahead and it pulls off the first item from the deck, if there is one. And if there is one, it calls execute on the thread pool executor. So this will go ahead and execute this runnable, which is stored here for various reasons, as we'll see. And that'll go ahead and execute that method. Now, what will happen here when this method, this is the method that's the serial executor's execute method. When serial executor method is called, it enqueues this, and then if mActive was null, in other words, we didn't have anything in the queue yet, schedule next is called to sort of prime the pumps to get things started. You'll also notice that schedule next is a synchronized method as well. And so these calls are all going to be done in a synchronized way. So we don't have to worry about there being race conditions on the deck. Notice that the deck is actually not thread safe. It's just a regular old array deck. So you'll notice what happens, what we're really doing here is we're queuing up items into this mtasks deck. And then if there's anything in there, we go ahead and, if there's nothing, if we don't have anything yet, we go ahead and start it to run. Otherwise, this thing gets run, and whenever schedule next is called back, it pulls the next item off the deck, if there is one, and goes ahead and executes it in a background thread. However, there's only ever one of these executions taking place at a time. And that's what the serial executor does. It makes sure that there's only one that's being executed at any given point in time. So that means that by default, in async, no matter how many async tasks there are, if you're calling execute, only one of them runs at a time. And they run to completion until they're finished because they're being executed here. Okay, so that's what serial executor does. So that you can tell that that's going to very much constrain the amount of concurrency, even though we're using the thread pool executor, because we're only calling one thing at a time on it. By default, the executor in an async task is the serial executor. You can see that being set here. And that means that by default, you have serialized behavior running in a background thread. That sounds a little bit contradictory at first, but that's just the way that things work with concurrency. We have a background thread that runs one thing at a time. But there's also a static handler, and this handler is going to be used to allow background threads to be able to communicate back to the user interface thread. And we'll see how that works later. Here is the implementation of this handler. So internal handler is a handler, and it goes ahead and is going to be created in the main thread. So it's going to create itself with the main thread's looper. And then whenever this guy gets called back, and we'll see how it gets called back later, but it's going to get called back when a background thread is going to send a message to the handler, which is associated with the foreground thread. And what that does is it takes the message and it casts the object field of the message to be something called an async task result. And we'll see that that's defined down here. We'll take a look at that in just a second. Async task result is basically just a place to park the async task object and the data that was passed to it when it was initially started. And we then go ahead and take a look at the type of the message. And if the message was a post result message, then we go ahead and we finish it, because that means that we're done. That's sending the result back to the main thread to execute inside of either the on post execute or on canceled method, or it's a progress update which came from publish progress, in which case we're going to call the on progress update method. And so we'll take a look and see how that works. So you can see that if it's a progress update, we call the on progress update hook method on the async task, which was squirreled away here, and we pass in the data that was passed back. Okay, so that's basically how we get things back to the UI thread from a background thread. And here's just async task result. This just keeps track of the data we need here. We have a couple of other sort of helper objects here. We have something called worker runnable, and a worker runnable implements the callable interface. Callable is part of the Java Executor framework, and callable is basically used to invoke a method in a background thread that runs as a two-way request. And so worker runnable is simply storing the parameters that are passed to the async task by execute. And these parameters will then be used concurrently in a background thread to know what to process, know what to call to the do in background method. And worker runnable implements callable for reasons we'll see shortly. There's also another important data member or field called mFuture, which is a so-called future task. And a future task is a very interesting object in Java, Java concurrency. It's in Java util concurrent. And a future task can be used to run a callable and then take its result and then get its result processed by a future. So you can basically set the result after it's done, so you can go ahead and pick the result up later after it's finished running. And you could also do other things to a future task, like you can query it to see if the result's done. You can cancel it if you want to. And so future task plays a very important role in this particular implementation. Here's the message post result and message post progress. I guess I should really be a little smarter and move that up here so it doesn't later. We'll stick it, where's a good place to put it? Let's stick it way up here at the very beginning. We'll just stick it up there. Those are just keeping track of what operations have finished. There's also a flag that's used to keep track of the status, and you'll see that status can be several different things. It can be basically pending, running, and finished. So those are the values you can have for status, and that's going to be used to see whether or not the async task is being used properly. Remember, you can only execute an async task once. And if you execute it again and it's already running, it'll be an error. If you try to execute it after it's done, it's also an error. Those exceptions will be thrown in that case. And we also have a couple of interesting atomic booleans. These are things that can be set and checked atomically without requiring any other locks, because they do locking internally using compare and swap operations. Here's an accessor method called getHandler that synchronizes on the async task to give it a critical section. Notice we have to use async task class because this is static, so we have to use the intrinsic lock from the class object itself. And this basically just checks to see if the internal handler has been initialized, and if it hasn't been initialized, it initializes it. In either case, it returns the initialized handler. Here's a method that's just used to set the default executor. Notice that this is hidden, so you can't actually access this as an application developer. It's only used internally by the library. Here's the AsyncTask constructor. This does some interesting things, and it's a little confusing at first, but I'll break it down and explain it. So the AsyncTask constructor creates a worker field that is a worker runnable, and worker runnable is parameterized by the parameters that are passed to execute, and of course also to do in background, and the result that do in background returns that's also passed to the on post execute. When this is called, so this has a method called call, and so if the call method is indeed called, which occurs if everything goes successfully, then we set the atomic boolean to indicate the async task has been called. We then set the priority of the background thread to be low priority. So if you don't like the lower priority, then you have to change that in your do in background hook method. And then the do in background hook method gets called. Now keep in mind, this call is taking place in a background thread. This is not taking place in the UI thread. This is taking place in a thread that's part of the thread pool executor, either the one that comes out of the box or one that you made. And it's going to call do in background with the parameters, and then it's going to pass that to this method called post result. And we'll see post result in just a second. Post result is what's used to get a result back to the UI thread by calling the on post execute method. Actually, what it does is it actually posts a message back to the handler that's used by the UI thread. That's an example of how AsyncTask is actually using the Hammer framework under the hood. We then have new future task. So new future task encapsulates this worker runnable, which is actually a callable, and that's going to be used by future task to run this in the background. And future task then has a done method, and the done method always gets called. This gets called when after we're finished, whether or not the call method succeeded or failed. No matter what happens, done gets called. And this will then go ahead and post a result if the AsyncTask call method is not in fact invoked. How could the AsyncTask method call method not be invoked? If you end up canceling the AsyncTask before its call method gets invoked, then it will not directly be called. So post result, if not invoked, is going to handle that particular case. So let's go take a look and see what happens with what post result, if not invoked, does. And this will then go ahead and check to see whether or not the async task was in fact invoked. And if the async task was not invoked, then we're going to go ahead and post this result. And the reason for that is we always have to give a result even if we've been canceled. So you'll see in a second how post result works. So what post result is going to do is post result is going to go ahead and go to the handler, which is associated with the UI thread. It will get a message, and it will call that message post result, because we're posting the result, either success or failure. And then we're going to go ahead and make a new async task result object, store that as the object parameter to the message we're making, and we're going to pass in the async task and the result as the parameter to this object, to this async task result object. And this new message will then be used to send back to the target. And what send to target does is it basically sends a message using the Hammer framework. It sends this message back to the target. And of course, the target in this case is going to be the internal handler, which is actually running in the user interface thread. So that's how post result will go ahead and send a message back to the target, which is the UI thread. All right, here's the execute method. You can see by default, execute takes the variadic parameter list, and it calls execute on executor with the default executor, which is the serial executor, along with the parameters. So no matter what happens, no matter what you call, execute on the executor gets called with an executor. By default, it's the serial executor. However, you can explicitly call execute on the executor with an executor of your own choosing. So sometimes that would be the AsyncTask thread pool executor. For assignment number 2, it's going to have to be the thread pool executor that you make that has the right parameters that you're going to need for your assignment number 2. It has to have a fixed size thread pool with bean count number of threads, no timeout, and a blocking queue that that's used to queue things up if you need it. You don't really need it, but if you did need it, that's what it would be there for. Now, what will happen when you call execute on the executor is it checks to see the status flag. And if the status flag is not pending, which means we haven't started our work yet, then we check to see whether it's running or finished, and we throw the appropriate exception. Because you're not allowed to execute an already running task, and you also can't execute a task after it's been finished. After we're all done with that little check, we then set the status to be running, and the on pre-execute method is called. Note that on pre-execute is called in the context of the user interface thread. So it goes ahead and calls on pre-execute. Now, as we'll see in a second, on pre-execute defaults to a no-op. So by default, nothing happens. It just is a no-op. But you, of course, can override that to do something else. We then go ahead and set the params field of the mWorker to the params that are passed in here to the execute on executor method. And then we go ahead and we say, hey, executor, please execute the future. Remember, the future holds a reference to the worker. And so this is going to go ahead and queue up the future task object on the executor's queue. And whenever there's a thread ready to run, the thread will pull that it'll pull that future off the queue, and it'll invoke its call method. And actually, first it invokes the run method of the future. The future turns around and calls the call method. The call method will then go ahead and do what we showed up here. It'll go ahead and set the task invoked to true and invoke the do in background method in the background. And we'll take a look at that in a second. And then it'll go ahead and it'll post the result back to the UI thread, if all goes well. If things don't go well, then we'll ultimately end up getting it back through an on-canceled invocation later. So that's how things get executed, and that's how they get stuck into the thread pool executor's work queue to be processed in the background. Let's take a look at some other methods. There's a method called getStatus, which is just used to get the status, whether it's running or pending or finished. We have the do in background method. This is the one you have to implement. It's abstract, so you've got to implement it. And that's what you do to run in the background. Here is on pre-execute. This gets called in the foreground. Notice it's a no-op by default. Here's on post-execute. On post-execute gets called in the background. I'm sorry, gets called in the UI thread after we're finished with running things in the background. And we'll take a look at how that works shortly. This is, of course, also a no-op. Here is on progress update. This gets called back if you call publish progress. See how that works in a second. And that's the on progress update hook method. Here's the on canceled method. On canceled, we'll simply go ahead and call back to the on canceled hook method. And that's where you do things that you want if things get canceled. There's a couple of helper methods that can check to see if methods were canceled or not. So is canceled just returns the atomic Boolean value that keeps track of whether or not this was canceled. And then here's the cancel method. So cancel is interesting. You're going to have to know how to do cancel for assignment number 2. So cancel is going to go ahead and set the canceled atomic Boolean to true. And then it's going to turn around and it's going to use the future to say, please cancel the operation if you're able to. And depending on whether you pass the may interrupt if running flag, that'll depend on how aggressively it tries to cancel things. Under the hood, calling cancel on a future will end up calling interrupt on the underlying thread. That's how it works under the hood. Here's a couple of methods that access the values of the future. You can either do a blocking get if you want to wait for the result, or you can also do a non-blocking timed get, which will block for only a certain amount of time. You can also execute runnables, which is kind of a goofy thing to do, but if you want to, you can do that. And then here's publish progress. You can see that publish progress, when you call publish progress, that will turn around and get yourself a new message, which is a post progress message, and it goes ahead and makes a new async task result with the values that are passed in and this async task, and it goes ahead and it does a send to target. So it'll go ahead and send those values back over to the internal handler where it gets run in the UI thread. And of course, it only does this if you haven't canceled the async task by this point. Here's the final method. This is the finish method. Finish is going to be called internally. Let's go take a quick look where finish is called. Here's finish. Finish is what gets called back in the user interface thread when a result has been posted. And as you can see, if the computation has been canceled, the onCanceled hook method gets called back. If the operation has not been canceled, the onPostExecute method gets called back. This always gets called in the UI thread. And then we go ahead and we set the status to finished to indicate that the async task is done, and any other calls to execute it will end up throwing those exceptions. Okay, so that was an explanation of async task, and it also hopefully gives you some pointers on how you can properly implement assignment number 2 with respect to the thread pool executor, and how you're going to have to find your own thread pool executor, because the one that comes out of the box doesn't do the trick that we need it to do. So you'll have to define your own, but you can do it somewhat along the same lines as the one that's actually part of the async task class. Okay, so with that, I'll be happy to take any questions that you may have. Let's see, somebody wanted me to post the link to Hashmap, which I will post after the session is over. And someone else wanted to know, is concurrent Hashmap put also atomic? Yes, of course, everything in concurrent Hashmap is atomic. So all those operations are done in a very, very clever way internally using compare and swap operations. In fact, I'll tell you what I'll do. I'll give you another link to look at. Let me find it. Let's see. Let me go ahead and share my screen here. So if we go and we search for Brian Getz concurrent Hashmap, we will find a very nice article that Brian wrote. Brian works at Oracle these days and has a lot of influence over the way that Java concurrency works. He also wrote a great book called Java Concurrency in Practice, and in conjunction with some other colleagues like Doug Lee and others. And so basically, this article explains how some of the internal implementation details of concurrent Hashmap work, and it's very much worth looking into, if for no other reason that you're unlikely to ever figure out how Java concurrent Hashmap works if you don't read this article, because it's just very, very mystical and very hardcore cool. Doug Lee wrote the bulk of it, and this is not the latest and greatest implementation. There's been some things that have been changed over time, but it'll give you a flavor for how they're able to do these really cool non-blocking operations in Java concurrent Hashmap. So most of the time in Java concurrent Hashmap, reads can all proceed concurrently. And oftentimes, even if you do writes, which are puts, into the Hashmap, those can often proceed concurrently as long as the values don't hash to the same location. And it's only if they happen to hash to the same location that you pay any overhead really at all in terms of weighting. And even that is done in a super optimized way using really cool compare and swap primitives that are part of the Java unsafe class. So it's really neat. Let's see, got some more questions. I have heard that AsyncTask is too old now. Not quite sure what it means to be too old. It does what it does quite nicely, so I'm not quite sure what that means. Last time we also talked about some downsides with AsyncTask. Let me go see if I can bring up those slides really quickly and go through them with you, because this may be what the earlier question about too old meant. I guarantee you AsyncTask is absolutely not too old. That seems like a silly thing to say. But let's take a look at the, see if I can find those slides that we're talking about, the drawbacks. A lot of people's perceptions of the drawbacks with AsyncTask are because they don't really understand how to program concurrency in Android properly. And so there are a lot of people who get confused because of that. All right, let's see. So let's go ahead and share the screen. So here was the section. This was actually from last week's, last week's lecture from week number 2. I talked about some of the traps and pitfalls of AsyncTask, and here's a good link to go to find more information about AsyncTask. So one of the quote downsides of AsyncTask is that cancellation is voluntary. But hey, that's just the way it is, right? If you're using threads in Java, you're going to have to deal with voluntary cancellation. So you just have to be prepared for that. There's also these issues of dependencies on activities and potentially losing results when runtime configurations change. Those things are easily addressed by simply knowing how to use the model view presenter pattern. And then there's also portability issues having to do with the fact that the semantics of execute have changed over time. And that's just a matter of knowing how to use execute on Executor. So what I talked about last time was that model view presenter addressed a bunch of these issues having to do with dependencies and losing results if runtime configurations change. So if you use that pattern, things work well. And then the issues about cancellation and portability just require you to understand how Android works and AsyncTask works. So I don't see AsyncTask as being old. You just have to know how to use it. Gee, what a surprise! Just like everything else in concurrent programming. There's also a question about RxJava. Obviously, you can use RxJava. It doesn't come bundled with Android, and it also requires a different way of thinking about programming. Not a bad way, by the way. It's a cool way, but it's not the way that most people think about programming. And it certainly is not used in any of the Android source code whatsoever. So there's no use of RxJava in the Android source code, whereas you'll find an enormous number of examples having to do with AsyncTask and the Hammer framework. I don't have any plans to do anything on RxJava, but perhaps somebody else will do something on that. We're focusing on the kinds of things you get with Android out of the box. At some point, I will be adding some more material to some lectures somewhere on the Java 8 concurrency features, things like the streams package, which gives you a programming model that's actually not dissimilar to parts of RxJava, because it basically uses stream style processing. And that will be something I'll add at some point somewhere, but that of course won't be for Android for the foreseeable future, because Android doesn't support Java 8 yet, unfortunately. Okay, so looks like we may be done with questions. If there's any more questions, please go ahead and ask them very quickly because we're about to wrap up. What we'll talk about, the next virtual office hour will actually be on Thursday. And what we'll talk about on Thursday will be my solution to programming assignment number 1. And by that point, we will also have programming assignment number 3 out. And so I'll be happy to take any questions about that, as well as any questions about anything else that you may have about anything that you've been doing or questions about the video. Just to reiterate, the purpose of the live lectures is to give you a chance to ask questions. And so if you don't ask questions, I'm just going to assume that you know everything that we've been covering. If you ask questions, I'll be happy to take questions, but it's up to you to leverage that opportunity. Okay, so no more questions. Thanks for joining, and I will put these videos up shortly.